we know that, and if we're going to say it the way it probably says it in the book, we'd say if we have a right triangle, the sum of the squares of the legs equals the square of the hypotenuse. But you know it better as probably a squared plus b squared equals c squared, which is fine. As long as, phones away, please. Don't want to see any phones out. Phones away. Yes, I can. I want it away in your pocket. Don't want to, in class, do I need to be more clear about this? In class, I don't want to see them. I'm not a Nazi about it during every single situation, but when I'm going through material with you, the last thing I want to see is you on a phone, because you're just going to ask questions about it, and you're going to rob other people of my time, because you're not doing the due diligence, what you're supposed to be doing. So put them away. Okay, so a squared plus b squared equals c squared, which is fine, as long as you remember what a, b, and c need to be, right? C has to be the hypotenuse, if you're going to say it that way, which is fine. But you just got to always remember that. C is the hypotenuse. A and B are the legs. Okay, so C squared equals A squared plus B squared. There are some cases, now, most of the time with a triangle, if I just randomly pick a value of A and B and I calculate C, I'm probably going to get some square root. That's not going to work out to be an integer. But there are a few instances where all three of the sides are integers in a right triangle. We call those Pythagorean triples. The most common, popular one, and a very useful one, is 3, 4, and 5. Those numbers just happen to work out. So 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. And so those could be the sides of a right triangle then, couldn't they? 5 could be C, and 3 and 4 could be A and B. That's what we call a builder's triangle, for reasons I'll explain later. There are a lot of these Pythagorean triples, but really some of them get to be pretty bizarre. The numbers get to be pretty big, and they're not very useful. This one, the numbers are nice and small, and they're not too far apart. They're all pretty close to the same size, and so that's one we use a lot. What would I do here? Now, just a quick review. We've done a lot of this already this year. What would I do to solve for x? Yeah, I'm going to set up the Pythagorean theorem to get an equation involving x that I could solve, right? So we could say 5 squared plus 12 squared equals x squared. 5 squared is 25. 12 squared is? And what's 25 plus 144?
169.
Okay, 169 just happens to be a perfect square. What? 13. Yeah, so if I square root both sides, and that's what I would do, of course, right? If I want to solve for x, I'm just going to get the x squared by itself and then square root both sides. So x equals 13. So we got another set of Pythagorean numbers, Pythagorean triple. 5, 12, and 13 could also be the sides of the right triangle. Then these happen to be integers. There are others, but those are the only two that you'll probably ever see. Okay, so what do we do in a situation like this, if I want to solve for x, where x is not the hypotenuse? Yeah, sure, just set it up. This time, the x doesn't start off on a side all by itself. It's linked with the 7. 7 squared plus x squared equals 14 squared. But I can still just pretty easily solve that equation for x, right? 14 squared is 196, 7 squared is 49, and then I get plus x squared. If I want to isolate the x squared, don't I subtract 49 first and then square root, right? So x squared equals 147. X is the square root of 147. We're not going to mess around with trying to spend time simplifying radicals right now. We've practiced that, we know how to do it, but it honestly isn't that useful. The square root of 147 is an exact answer. I could put that in a calculator and get a decimal if I want to. So what I'm going to typically ask you to do in chapter 9 in situations like this is either I'll just ask you to write this. If I ask for a perfect answer, you're free to just say the square root of 147. You don't have to simplify it if I want an exact answer. Most of the time I'm just going to ask you to round it and give me a decimal anyway. So just put it in a calculator and round the answer to 2 decimal places. Okay. All right, so now how could I tell? Now I'm going to challenge you a little bit here. How could we verify whether or not those triangles are right triangles? What do you mean?
If the sides are all equal to each other, it's so.
Well, we have to do something with the sides. Yeah, not exactly equal to each other, but something with the sides. How can I check, for example, that top one to see if it's a right triangle? What do you think? Yeah. Okay, yeah, so we could just check and see if it actually does adhere to that Pythagorean relationship, right? Now, I have to always choose, when I plug this stuff into the Pythagorean theorem, I got to make sure I'm plugging the longest side in for C. So what is the longest side up here?
The square root of 113.
Square root of 113. How do I know that? How do I know that? Say it again. Ah, okay, there's a good way to do it. 8 is obviously bigger than 7. So the only contender, the only other contender for the biggest side would be 8. 8 squared is 64, right? And so the square root of 64 would be the number I would have to start with to get 8. I've got the square root of 113. 113 is bigger than 64, so it must be the biggest side. So then all I would have to do is just see if it works, right? 8 squared plus 7 squared, just check that and see if it is the square root of 113 squared. How do I square a square root? What happens when I square a square root? Yeah, it's actually very convenient. They undo each other. Squares and square roots are inverse operations. They undo each other. So if I square these out, the square root of 113 squared is just 113. 7 squared is 49. 8 squared is 64. 49 plus 64 is 113. So is it a right triangle?
Yes.
It is. That one works. Yes, it is. Okay, what about this guy? The other one. Okay, same thing, right? I have to just check these and see. Is 4 times the square root of 95 squared equal to 36 squared plus 15 squared? Well, how do I square it? How do I square that? How do I square 4 times the square root of 95? Okay, raise your hands. Raise your hands. You got an idea? What do you think? Back here. Yes, ma'am. Say it again. I could mean on a calculator. I could. What if I don't have a calculator? What can I do? Oh, okay. Okay, good. So, yeah, so we could distribute, when I've got two things that are a product of two things that's being taken to a power, I can distribute that power to both parts, right? Now, if I don't remember that, there's an easy way to think about this. Mike, let's get everybody, thank you. So, there's an easy way to think about this. When I take this, the quantity 4 times the square root of 95 squared, what does it mean to square something? Multiply it by itself. So really what I'm doing is I'm multiplying 4 times the square root of 95 times 4 times the square root of 95, right? Right now, when I multiply a string of 4 things together like that, does it matter the order in which I multiply them? It doesn't. I can multiply 4 things in any order I want to, right? So why not multiply the 4 times the 4, right? That's 4 squared. And then the square root of 95 times the square root of 95, right? That's 95, okay? Does that make sense? So that's, you can always kind of remember how that works. But there is, and we'll go through these properties again next year a lot, but we do have that property where we can distribute a power. So we get 16, 4 squared is 16, square root of 95 squared is 95. 16 times 95 is 1520. Yeah. Now if I look at the other side, 15 squared is 225, 36 squared is 1296. AJ, please don't. If I add those up, I get 1521. Okay, so is that a right triangle? Very close, but it's not quite. Very, very close. You could, if you drew this thing exactly, if you had this thing drawn exactly to scale, there's no way you could tell by looking at it whether it were a right triangle or not. It's just too close. But when we check the Pythagorean theorem, we see that it's not. Okay, so now another question crops up then. What if we wanted to do more than just verify if it's a right triangle or not? What if we want to determine if it's not a right triangle, what is it? And if we're gonna classify triangles, and we talk about a right triangle, we're classifying the triangle by its biggest angle. It's a right angle, right? What are the other two alternatives?
Scaling and obtuse.
Okay, now, if I say say it again,
Scaling and obtuse.
not scaling and obtuse. If I say
Oh.
scaling or isosceles, I'm classifying by sides. If I wanna classify by
Oh,
angles,
acute.
acute or obtuse. Right, now what's it mean to be an acute triangle?
Lower than 90. Lower than 90.
Okay, it means that the smallest angle, or the biggest angle, sorry, is less than 90, right? So all three angles are less than 90. If it's obtuse,
It's bigger than 90.
then the biggest angle is bigger than 90. So really, the right triangle is just kind of the boundary between those two conditions. And so if I wanted to see what this thing really is, I would just have to compare this situation to the situation if it were a right triangle, right? Does that make sense? Now, this is what's going to happen here. If we calculated what a squared plus b squared should equal for this to be a right triangle, the hypotenuse should be, the square of the hypotenuse should be 1521, right? But it's not. It's only 1520. So what does that mean?
That it's acute.
Doesn't that mean it's acute? Right? You see that? Here, let's real quickly. Let's demonstrate that. There's a way we can do this here. This will be good. Okay, so let's use Geometer Sketchpad here for a second.